So in this video, we are going to talk about introduction to mathematical induction. And at the end of this video, we are going to understand how you can use mathematical induction to prove a statement. Okay, so let's look at something. To illustrate how induction works, we are going to do some imagination here. Imagine that you are climbing an infinitely high ladder. And the question is, how do you know whether you will be able to reach an arbitrary high rank? Suppose you make the following two assertions about your climbing ability. So these are the two assertions. And the first one is, I can definitely reach the first rank. And the second one is, once I get to any rank, I can always climb to the next one up. Let's look at something here. If both statements are true, then by statement 1, you can get to the first one. And by statement 2, you can get to the second one. By statement 2 again, you can get to the third and the fourth. Therefore, you can climb as high as you wish. Let's note something. Notice that both of these assertions are necessary. For you to get anywhere on the ladder, if only statement 1 is true, you have no guarantee of what getting beyond the first rank. Because if you can definitely read the first rank, if it's true, there's no way, it's not guaranteed that you can get to this second one, right? Yes. If only statement 2 is true, you may never be able to get started. Because once you get on any rank, I can always climb to the next one. But you need to first get to the first rank before. So if only statement 2 is true, there's no way, you understand? There will be, you will never be able to get started. So let's make some assumptions here. Assuming the ranks of the letters are labeled as what? Positive integers. 1, 2, 3, 4, 5, 6, 7, dot, 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 because it's infinite. Now think of a specific what? A specific property that a number might have. Instead of reaching an arbitrary high rank, we can talk about arbitrary positive integers having that property. We'll use the shorthand, which is P of n, to denote a positive integer. So this is a positive integer, right, of n having a property of p. So this, when you see P of n, is a positive integer of n having a specific property of what? P. How can we use the ladder climbing technique to prove that P of n is true for all positive what? Integers, positive n, which n represents the number of steps. The two assertions we need to prove are, the first one we're going to prove is, if P of 1 is true, that means that when you substitute 1 into the equation given to you, it should be true. And for any positive k, if P of k is true, then P of k plus 1 is also true. That means that, how do we link this one to it? If I can climb, or if I can reach the first step, then once I get to any rank, I can always climb to the next step. Because if I'm able to make one step, then if this one holds, that means I can climb to the first step. But with one doesn't guarantee me that I can also move to the second step. But if I bring in the second condition, which is once I get to any rank, I can always climb to the next one, that means that I can also go as high as I want. So foundation for argument of this type is the principle of mathematical induction. Let me change my screen, which can be used as a proof technique on statements that have a particular form. We can state it in this way. Let's pay attention here. a proof of mathematical induction that a proposition P of n is true for every positive integers n consists of two steps. So we have two steps. The first step we are going to talk about is the base case. The base case. And when we talk about the base case shows that the proposition P of 1 is true. So P of 1 is true. And then we have the second one, which is what? The inductive state. The inductive steps. The inductive step. For the inductive step, right, we assume that P of k is true. So P of k is true, choosing a positive integer k, and show under the assumption that P of k plus 1 is also true, must be true. So in this case, if P of k is true, then we also assume that P k plus 1 must also be what? True. So now let's take some example and work with that. So first example you're going to take, let me change the screen. So the first example you're going to take is that the following proposition is true for all integers. So we have example 1. Example 1. So P of n 1 plus 2 plus 3 plus 1, 2, 3 plus n is equal to n bracket will be n plus 1 all over 2. So for that, we need to know we have two steps in this, the base case and the inductive step. So let's look at the base case. So for the base case, we know that you must prove that P of 1 is true. So in that case, what you do now is that you're going to put 1, you're going to equate this n is equal to n plus 1 all over 2. Then you substitute in with what? 1. So let's do the substitution. 1 is equal to 1 bracket will be 1 plus 1 all over 2. So 1 is equal to, this is going to give you 2 over 2, which gives you 1 is equal to 1. So for the base case, you know that for this statement, P of 1 is true. Then we move on to the inductive state, the inductive step. Let's move on to the inductive step. So for the inductive step, we have two things to do. The first one is that we assume for what? The integer k. So let's assume for the integer k. So we first find P of k. So what you do now is that it's just substitution, putting k into the statement given to us. So 1 plus 2 plus 3 plus 1, 2, 3 plus, then we have k is equal to k bracket open, k plus 1 all over 2. And then we'll show that if P of k is true, then we will find what? P k plus 1. And so we are going to do some substitution here. So we are going to have 1 plus 2 plus 3 plus 1, 2, 3 plus, this is going to give you k plus 1 is equal to k plus 1, k plus 1 plus 1 all over 2. Now I'm going to break down how I attain this. So for the P of k plus 1, proving it that you need to prove it and get a simplified one. So what you do now is that let's do the proving here. Let me bring it down. So first, what you need to do is that proof of what? Inductive step. You are going to do proof of inductive step. Proof of inductive step. So by the induction hypothesis, we already have a formula for what? The first k of integer. That's when we substitute in with k. So A formula for the first k plus 1 integer may be found by simplifying adding k plus 1 to both sides of the equation. So what it means is that we are going to have this. We are trying to prove it. So we have 1 plus 2 plus 3 plus k plus 1 is equal to k bracket open k plus 1 all over 2 then plus k plus 1. What you do now is that after we having k plus 1, we are going to add the k plus 1 into this side and also add it to what? This side. As very simple as that, because when you go to the first one, what we did for the key, let's look at the key. For the key, we had what? This k bracket open k plus 1 over 2. So what you do now is that for us to find the inductive proof of inductive step, you add k plus 1 to this side and also add k plus 1 to this side, as we did here. So k plus 1 to this side, k plus 1 to this side. Then you simplify. So let's do the simplification. I hope you understood that. So for the simplification, what you do now is that you are going to simplify this side. So for the simplification, you're going to have that. Let's use our normal mathematics. So you're going to have k into bracket k plus 1 plus what? 2k plus 1. And this is going to give you the LCM, going to give you all over 2, because you're going to have 2 and 2 going to self 1, then times k bracket open k plus 1, and here 2 going to 1 going to 2 times and 2 times that. So we have this. Then we simplify. When we simplify this, we are going to get k squared plus 3k plus 2, and we have all over 2, right? And we can use expand this, and then you get a value which is going to give you k plus 1. You know how to do this expansion, and k plus 2 all over what? 2. So in that case, after getting this right, you're going to simplify it again. Now you want us to, you see, when we inserted the k plus 1, our answer that we had was this. Which is the answer. But we are trying to prove it from here that the answer we had was correct, is the same as this. So after getting your answer, you try expressing your answer in this form. So if you can come here, this answer can be expressed as this: k plus 1, then this is going to give you k plus 1, then plus what? 1, and you close the bracket, and all over what? 2. That's the easiest way to do the mathematical induction, because even the answer is already there, but you need to just prove that it's the same thing, because this is the same thing. When you do the substitution, you're going to have the same answer. So by the proof of the inductive step, you should get the same answer. If you don't get the same answer, that means that there's a mistake with it, right? Let's try another one. Right, example 2. We need to prove that p of n is equal to, it donates that 1 plus 3 plus 5 plus 1, 2, 3 plus bracket open 2n minus 1 is equal to n squared. You can pause this video to try on hands-on. So let's go. So we have 2 steps in dealing with mathematical induction. The first one is the basic case. That's a base case. But let's look at something. Now they give us a condition that therefore the sum of what? First n odd integers is n squared. Look at this. So the question is, after giving this, they give a condition that the sum of the first n odd integers is what? N squared. Show that p of n is true for all positive integers n. So we are going to start with the base case. That's one thing I love about it. I always love the base case. So with the base case, we need to do p of 1, and we try that it should be true, right? We are going to take this and equate. You have 2 bracket open 1, then minus 1 is equal to 1 squared, and this is going to give us 1 is equal to 1. So the base case is true. P of 1 is true. After doing the substitution, we had it to be 1. Then we go to the inductive state. So the base case, let's move on to the inductive step. For the inductive step, we already established that we have 2 steps, which is first one, we are going to prove that P of k is true. So with that, you're going to do some substitution. 1 plus 3 plus 5 plus 1, 2, 3 plus, here you're going to give us 2k minus 1 is equal to k squared. This is the first one. And with the second one, we're going to prove that if P of k is true, then if P of k is true, then P of k plus 1 must also be true. So we do some substitution here. So it will be 1 plus 3 plus 5 plus 1, 2, 3 plus, this is going to give you, first you're going to write this, that will be 2k minus 1, then plus, we are going to substitute k plus 1 into this. So let's do that. When you substitute, you're going to get 2 brackets open, k plus 1, then minus what? 1. And in that case, when you do expansion, you're going to get 2k plus 2 minus 1, and you're going to get 2k plus 1. So here it's going to give you 2k plus 1, and it's going to give you k plus 1 all squared. I hope you understood that. Now let's do the proving. As we said that we are going to take this, you first, for the proving, now we know that our answer, that after expansion we should get this answer, right? This answer. So let's do that. So for our answer, we are going to prove the inductive step. So let's go to the proof. So, and for the proof of inductive step, to get this answer, what you need to do is that we are going to take the first condition, which is P of k. We have this. So what you do now is that let's write 1 plus 3 plus 5 plus we are going to take this, right? So we're going to take 2k minus 1, and then let me bring this equal to sign here, k squared. And what to do now is that you are going to add 2k plus 1 to each side. 2k plus 1 to each side, because that's what we had for the k plus 1 is 2k plus 1 for each side. So always what you need to do is that for the proving, after the substitution of k plus 1 into this equation, that's into this statement, that's from k, we had 2k plus 1, we are going to just bring it here. We had this from here. So for us to prove the inductive step, which is P of k plus 1, what you do now is that you just bring in this, the substitution. After you substitute into this is what you had. You just bring it to the other side. So you add this 2k plus 1 to this side, and also you add 2k plus 1 to this side. I hope you understood that. Then you are going to focus on this and simplify. I hope you had that. Let me go again. What you do now is that for the first one, P of k, we had it to be 2k minus 1 is equal to k squared. And then P of k plus 1, you do substitution into this equation. So you put it inside. So what you do now is that you're going to repeat this itself. You're going to repeat it and then put the k plus 1 into it. And you're going to get 2k plus 1. And it's equal to what? K squared, it's going to give you k plus 1 all squared. And then for us to prove it, what you need to do is that you take the first inductive step, which is k, and then add 2k plus 1 to each side. Because how do you get a 2k plus 1? After substituting k plus 1 into it, you're going to get 2k plus 1. When you do the substitution, I've proved that here. Let me go to the top to show you. We had 2k plus 1 after the substitution of k plus 1 into this, and that's why we had this, right? So for us to prove it mathematically, using proof second prove it, you're going to add 2k plus 1 to each side, and then we'll concentrate on this side and work out with it. And the secret aspect is that we know that we're going to get k plus 1 squared. So let's simplify this. Simplification, let's go with k squared plus 2k plus 1. And when you do it correctly, then you're going to get, after simplifying this, you're going to get k plus 1 squared. Because this one, you're going to get k plus 1 and k plus 1. In this case, you're going to get k plus 1 squared. It is very binomial expansion. This is binomial expansion, and when you do that correct, you're going to get k plus 1 squared. Very simple like that. So that k plus 1 is true. When k is true, then p of n is true for all natural numbers, right? Yes. So let's look at example 3. For example 3, the question is that p of n denotes that 1 plus 2 plus 2 squared plus 2n is equal to 2n plus 1 minus 1. And this is saying that show that this is true for all non-negative integers. And with non-negative integers, it includes what? It includes, this includes 0. So in this case, since it's a non-negative integer and it includes 0, we can start our base case and take it from 0. So our base case, we can find p of what? 0. And p of 0 should give us 1. And if it's equal to 1, then it is true. So now let's do that. So always, sometimes they can give an interval, but what you must know is that the interval you are taking, when you put inside the statement given to you, you should get what? 1. That means that you can continue with the what? The inductive what step. So let's prove it. So with this, you're going to get 2 exponent 0 is equal to 2 exponent 0 plus 1 minus 1. And this is going to give you 1. And this is going to give you 2 exponent 1 minus 1, which will give you 1 is equal to 1. So it is true for the what? The base case, because this is a non-negative integers. And non-negative integers, it starts from 0, 1, 2, 3, 4, 5. So it includes 0, and you can do that, right? And prove that. So now let's continue. Then we are moving on to the inductive step. So for the inductive step, inductive step. So for the inductive step, what you do now is that we assume that p of k is true. And when we assume that, you're going to get 1 plus 2 plus 2 squared plus 1, 2, 3 plus 2k is equal to 2k plus 1 minus 1. I hope you understood that, because this is n plus 1 minus 1. So we've changed the n into k. And then for p of k plus 1 is also true. And we're going to have it in a way that you're going to get 1 plus 2 plus 2 squared plus, we are going to repeat this, right? So we are going to repeat 2k, then plus 2k plus 1. I hope you understood that. Is equal to, now we are substituting k plus 1 into this, right? So in that case, doing k plus 1, we're going to get is equal to 2 brackets open, k plus 1. Then you close this bracket, plus 1. You close the bracket. Then minus what? 1. I hope you understood that. It's just some substitution that we did here. We are replacing the k with what? K plus 1. That's what we did here. That's why we have it here. And we are repeating the same thing. So for the second one, you repeat the same, and then you put k plus 1 into the equation, into the statement given, and you do the same. But the second thing is that you are going to repeat this for here and you substitute in k plus 1. But for the other side, you are not going to what? Repeat this value, which is this statement. I hope that is very clear for you. Let's continue with the step. What to do now is that let's try to simplify this, right? So for simplification, you're going to get, let me write 1 plus 2 plus 2 squared plus 1, 2, 3 plus 2k plus 2k plus 1 is equal to this one. When you simplify it, what are you going to get? You're going to get 2k plus 2 minus 1. Now, when you get this, that means that that is your answer. So when you prove it using the inductive step, you should get what? 2 exponent 2k plus 1 minus 1. Now let's move on to the proof. For the proof is very simple. What you do is that you just take this one, which is the inductive step, first one, p of k. So you're going to take it, and then you are going to add, when we substituted, what did you get? We had what? 2k plus 1. I getting 2 exponent k plus 1. That's what we had here. So you are just going to add this to this side and add it to this side. So what you're going to get is that you're going to get 1 plus 2 squared plus 1, 2, 3 plus 2k, then plus this one, 2k plus 1, and is equal to, you write this, 2k plus 1 minus 1, then plus the 2k plus 1. And then you concentrate on this. So your aim is that when you solve this, you should get this one. And that's make sure that when you get this one, that means that it is true for k plus 1 when k is also true. So let's prove that. So what you do now is that let's take this and simplify it to see whether we'll get the answer, which is 2 exponent k plus 1. So let's do it. So with this, you're going to have that you're going to get it bracket open 2k plus 1 minus 1 plus 2 exponent k plus 1. Let's expand it. When you expand, going to... So with this, by factorization, we can do it in a case that this one, we can factorize the 2 out, which will be 2k plus 1, then times our 2, then minus what? 1. So at this time, this will give you 4k plus 1.